Have you ever stopped to think about how your email actually finds you? Or how a video streams perfectly to your phone out of literally billions of devices online? Well, it's all thanks to this invisible address system running the show. Today, we're going to pull back that curtain and deconstruct the internet's address book, IP addresses, and the incredible art of subnetting.
Okay, think about it like this. You have a mail carrier, right? They're trying to deliver a package to a huge apartment building. Now, the building has one single street address, but inside there are hundreds, maybe thousands of individual apartments. So how does that package get to the right door? That exact problem is what IP addressing and subnetting solve for the internet, getting data to one specific device inside a much larger network.
So here's our game plan. First, we'll cover the basics of the internet's address book. Then, we're going to learn to speak the computer's native language, that's binary. After that, we'll see how addresses are built with networks and hosts. Then, we'll uncover the secret job of something called the subnet mask before we get our hands dirty creating our own custom networks. And finally, we'll put it all together and see why any of this really matters. Let's jump in. All right, so let's start with something we all get. We're going to take that familiar idea of a postal address and see how it maps almost perfectly to the language of the internet. Here's the big secret. Every IP address, a number like 192.168.1.1, it's not one address. It's actually two addresses smashed together. One part identifies the street on the internet. We call that the network. And the other part points to the specific house on that street, which is your computer or your phone. We call that the host. Street and house. Network and host. Simple as that. Now, to really understand these IP addresses, we've got to see them the way a computer does. See, computers don't think in numbers from 0 to 9 like we do. Their whole world is just on or off, ones or zeros. They speak in binary. I know this might look a little intense, but think of it as a set of 8 light switches. That's it. Each switch has a value, starting at 128 and going all the way down to 1. If a switch is on, if there's a 1 in that spot, we count its value. If it's off, a 0, we just ignore it. So this string of ones and zeros, it's really just a secret code for a number we already know. So let's go ahead and crack that code from the last slide. We take our binary number, 011101111, and we just look for all the on switches, the ones. Their values are 64, 32, 16, 4, 2, and 1. Now for the easy part, we just add them up, and what do we get? 119. It's literally that simple, and that's how computers translate their basic on-off language into the numbers that we use every day. Okay, now that we can speak the language, let's take a look at the original blueprints for how these IP addresses were designed. We're talking about the different address classes. So the folks who first designed the internet, they came up with 3 main classes, A, B, and C. And each one just splits the network part and the host part differently. Class A uses just the first number for the network, leaving the other 3 for hosts, perfect for a tiny number of gigantic networks. Class B splits it right down the middle, 2 and 2. And Class C uses the first 3 numbers for the network, leaving only 1 for hosts, which is perfect for having millions of little networks. So what's the real difference here? Honestly, it's all about scale. A Class A network is like having an address for an entire state. One network that can hold something like 16 million different devices. It's massive. A Class C network, on the other hand, is more like a single residential street, with room for just 254 devices. They were built for completely different jobs. Okay, so you might be thinking, hey, if I can tell what class an address is just by looking at the first number, why do computers need anything else? Well, that's a great question. Computers need a special tool to do the math for them, like a secret decoder ring that lets them officially separate the network part from the host part. And that tool is called the subnet mask. The subnet mask uses a really simple piece of binary math called a logical AND. Just think of it like a very strict doormat at a club. The rule is simple. The result is a 1 only if both of the numbers coming in are a 1. If either of them is a 0, the doorman says, nope, and the result is a 0. And here are all the possible combinations. See? 1 and 1 is the only way you get a 1. Everything else, 1 and 0, 0 and 1, 0 and 0, they all equal 0. This incredibly simple little operation is the entire key to how subnetting actually works. Okay, let's see this in action. The computer takes the IP address and the subnet mask and it lines them up, one on top of the other, in binary. Then it just does that simple AND operation column by column.
But look at the mask. It's all ones over the network part and all zeros over the host part. It acts like a stencil. Wherever the mask has ones, the original IP address bits are saved. But where the mask has zeros, it just wipes out the host information completely. And what are we left with? The pure network address, 192.100.10.0.
All right, now for the really cool part. We've learned the rules of the system. Now we're going to learn how to bend those rules. This is the art of subnetting, taking a standard off-the-shelf network and carving it up into smaller, custom networks that fit exactly what we need.
Let's try a real-world problem. Imagine you're the network admin. You've been given one standard network, 192.10.10.0, but you need to create 14 separate networks for 14 different departments, and each of those needs room for at least 14 devices. How in the world do you do that?
The answer, the secret trick, is to borrow some of the bits that were originally set aside for the hosts, and we reassign them to the network side of the address. This is what lets us create more networks than the default. And for this specific problem, the magic number of bits we need to borrow is 4.
So why 4? Well, the math is actually really simple. The number of subnets you can make is just 2 to the power of the number of bits you borrow. So in our case, 2 to the power of 4, that's 2 times 2 times 2 times 2, gives us 16. We needed 14 subnets, so getting 16 is perfect. We have exactly what we need and a little room to grow.
So what's the result of us borrowing those 4 bits? Well, we have to change our subnet mask to reflect the new reality. Instead of that default mask ending at a 0, we have to turn on the first 4 bits in that last section. And if we add up their values, 128 plus 64 plus 32 plus 16, we get 240. This new custom mask is what tells every single device on our network about our brand new smaller subnetworks.
We've been pretty deep in the weeds on how to do all this, but it's so important to understand why. Why do network pros go through all this trouble? Well, it's all about bringing efficiency, security, and a little bit of order to the digital chaos.
Look, subnetting is absolutely essential for any modern network. It boosts security by letting you wall off your important departments, like finance, from, say, the public guest Wi-Fi. It cuts down on network chatter by keeping traffic contained in its own little neighborhood, which speeds things up for everybody. And it just makes a network administrator's life easier, letting you fix problems in a much smaller, more manageable area. It's how we keep big, complicated networks running like a well-oiled machine.
So we've seen how we can cleverly slice and dice the addresses we have to make them fit our needs. But this whole system we've been talking about, IV4, it has a finite supply of addresses. So that leads to a pretty huge question. What happens when the entire internet starts to run out? Well, that is a story for another explainer.